Welcome to exercise 3. In this exercise, you will be exploring 8 different polynomials. Some are given in factored form, some are given in standard form. And what you'll want to do is use what you've learned so far about polynomials, about factors, about exponents, about x and y intercepts, to try and identify for each of these polynomials what their x and y intercepts are, what is their degree, even can you get the ones that are in standard form, so 3, 6, and 8, can you get those into factored form? And ultimately, can you match each of these 8 with the graphs that are given in your packet? This exercise will challenge you quite a bit, and you will need to problem solve and get creative, but no calculator yet, okay? It's okay if you are at a loss for some. Maybe some you'll get by the process of elimination. But do what you can, and then unpause the video for the next step. Well, now that you have explored and exhausted your options, the next step I'd like you to do is take your graphing calculator, and I'd like you to check each of these polynomials in your calculator to see if you got the right graph. As you do, either confirm your intuition or revise your understanding. And as we move along, I will also be pointing out some of the things that you might have noticed along the way. Alright, it's time. Let's look at polynomial 1. Polynomial 1 is a cubic. It belongs to the cubic family because there are 1, 2, 3 factors. X minus 2 is only repeated once, but x plus 5, because of the square, is repeated 2 times, and that makes a total of 3 linear factors. That makes this a cubic. And even though it's a cubic, it actually only has 2 x-intercepts because there are only 2 distinct factors. So negative 5 and positive 2 are the 2 x-intercepts. The y-intercept you can also get from the factored form, but you have to do a little calculation. To find the y-intercept, remember that you need to find p of 0. So you need to plug in 0 for x, which here means that 0 minus 2 is negative 2, and here 0 plus 5 is 5 squared. And since 5 squared is 25 times negative 2 is negative 50, then the y-intercept is negative 50. The proper graph then that matches these characteristics is this one. And here you'll notice the y-intercept is down here at negative 50. Okay, right there's the y-intercept. And there are 2 x-intercepts at negative 5 and at positive 2. You may also notice and remember that when a factor is squared, that the x-intercept has a certain characteristic, and that would be that the vertex, that sort of high point of the graph, sits right on the x-axis. Ultimately here, to describe in words the shape of this graph, we would say that the graph increases until it reaches a high point at negative 5. Then it decreases from negative 5 to 0. And then it increases again from 0 on. The turning points are the high points and the low point here, and that's where it changes direction. Now on to polynomial 2. Polynomial 2 has 3 linear factors, x minus 2, x plus 2, x minus 3, and therefore has 3 x-intercepts 2, negative 2, and 3. But it also has this lead coefficient. So what is the role of the lead coefficient in this cubic polynomial? If we identify the graph for this polynomial, you'll notice there's our x-intercepts, negative 2, positive 3. The 2 comes in then when we try and calculate the y-intercept. So what is this y-intercept over here? Well, if we plug in 0 for x, the first factor will turn into a negative 2, the second factor will turn into a positive 2, and the third factor will turn into a negative 3. And if we just multiply those out, we would get negative 2 times 2 is negative 4, times negative 3 is positive 12. But notice that positive 12 would be more down here. In fact, to find the actual y-intercept, we still need to multiply by that 2. And therefore, 12 times 2 is 24. That's the actual y-intercept. So the role of this 2 is actually to stretch the polynomial, to make it steeper, and in this case, it doubles the y-intercept. Okay, it does not change the x-intercepts, those are set by the factors, but it does double the y-intercept. Compare that polynomial quickly with these other two polynomials that have the same factors, but the first one does not have a lead coefficient, or we could say the lead coefficient is 1. And here notice that the polynomial does not quite have as high of highs and as low of lows, and in fact the y-intercept is right at 12. A negative lead coefficient here, on the second example, would have a similar shape as the one we were given, but it is reflected upside down because of the negative, giving us, as you can see here, a y-intercept of negative 24, and the entirety of the graph is just upside down. Polynomial 3. What's different about this rule is that it is not in factored form, it's in standard form. So is there anything that we can tell about the graph from this standard form? Well, one of the things that we can tell is that the y-intercept is 0. And so you'll be looking for a graph that crosses through 0, 0. But I'll admit that this polynomial is a difficult one to identify. Can you find the x-intercepts? Just 0, 0. Can you identify the graph? Well, kind of. This is actually the graph for this polynomial, and notice that it does go through 0, 0. But also notice that because it's a quartic, so has degree 4, then we are looking for up to 4 x-intercepts, and this one has 4. We could take on then a reverse approach by actually testing certain x values to see if they equal 0. For instance, since this polynomial has an x-intercept at positive 1, we could test and see if 1 is what we call a 0 of the polynomial. So if we entered 1 for x, would this give us a value of 0? And let's see, once I'm done writing, that 1 minus 21 plus 20 is 0, giving us that x-intercept. You could repeat the process with the 4 over here and the negative 5 over here, and see that each of those values will also give the polynomial a value of 0. Can we then change this polynomial to a factored form? Well, perhaps, especially since we know now what the x-intercepts are. In fact, each x-intercept corresponds to a factor. Since it's quartic, we will have 4 factors. The x comes from the 0 x-intercept. The x minus 1 comes from the 1 x-intercept. The x minus 4 comes from the 4. And the x plus 5 comes from the negative 5. For polynomials 4, 5, and 7, let's try a matching activity. Let's see if we can match these three with these three graphs. And the easiest way to do that is by identifying x-intercepts. For instance, you'll notice that polynomial 4 has 1, 2, 3, 4 factors that give us 4 different x-intercepts. And those x-intercepts would be at -3, -1, +1, and +5. And by a quick inspection, you will notice that the second graph has those x-intercepts at -3, -1, +1, and +5. You will also perhaps notice that the square on the x plus 3 factor results in that turning point sitting right on the x-axis. And again, that's a characteristic that we want to be able to observe. The second polynomial, polynomial 5, only has 2 different factors, and that gives us 2 x-intercepts at 0 and at -4. And this graph right here has 2 x-intercepts at 0 and -4. You will also notice a lead coefficient of -0.1. The negative here has the effect of turning the graph upside down, and the 0.1 has actually the reverse effect, instead of stretching, of compressing the graph. Without that, this graph would be way, way higher, and the high point would be 10 times higher. You might also observe the cube. This is our first cubic factor, and which means that this is actually a quartic polynomial, because there's 1 factor of x and 3 factors of x plus 4, making a total of 4 factors. The cubic 0 has yet a different look than the squared 0, and that's also one that we want to learn to be able to identify. Polynomial 7 has 1, 2, 3, 4 x-intercepts, which you can see right here on this graph. Polynomials 6 and 8 are also in standard form, and kind of by process of elimination, we can try and identify which graph corresponds to each of those. But also then from the graph, we might be able to generate the factors. Polynomial 6 is actually factorable by hand. Let me show you the trick. First of all, you'll notice that there are only 2 terms, and therefore we can factor out an x squared from both of them. That leaves then an x squared minus 9. X squared minus 9 in turn can also be factored as x plus 3 times x minus 3. So this is our factored form, and notice that it corresponds to 3 x-intercepts at -3, +3, and 0 with the bounds. Polynomial 8 is much more difficult to factor, but you will notice the y-intercept here at +8 seems to match. And based on the graph, because we have 3 x-intercepts at -1, 2, and 4, with a bounce at -1, the proper factorization looks like this. Well, I hope you learned a few things about polynomials today, and keep learning, keep exploring. I hope this video was helpful.